Alright, so we're going to get started with a brief review and then move into a little bit of new content. So, the last class we talked about the O2 conformer and the net drive hypotheses. And so I showed some experimental evidence from Michael Hogan's group, published about 20 years ago, where they did manipulations to oxygen delivery, either by titrating down the inspired oxygen content or changing the arterial oxygen content by changing the inspired fraction of oxygen, or by changing muscle blood flow. So here we have arterial PO2, titrated down basically by changing the inspired fraction of oxygen and also by, in this case, decreasing muscle blood flow. And what we found in these examples is that when oxygen delivery through either changing arterial oxygen content or muscle blood flow was reduced, is that at a constant motor drive, remember this was the hind limb or gastroc of an animal, is that when that animal has a constant electrical stimulation, is that the VO2 declines and so too does the force output of that muscle. So regardless of how oxygen delivery was manipulated through content or blood flow, is that the muscle, the state of the muscle basically conformed in terms of its oxidative capacity. So the oxidative provision of ATP declined in relation to the amount of oxygen that was being delivered to the cell. So in other words, the muscle metabolic state or the performance of the muscle conformed to the oxygen status of the muscle. Again, and this is at a constant motor drive. And the take-home message was that the muscle did this as a means of trying to preserve its muscle metabolic state. So force output in VO2 was decreased in the setting of a reduced oxygen delivery, while indices of muscle metabolic perturbation, so phosphocreatine levels as well as muscle lactate levels, were relatively preserved across the different oxygen delivery conditions. So, if the muscle's first choice, in this case, is to decrease its force output, decrease its rate of oxygen consumption at a constant motor drive as a means of trying to maintain or prevent disturbances in muscle metabolic state. Okay? We also showed some evidence in humans where they did the electrical stimulation of the adductor pollicis muscle, so the thumb muscle, where they changed perfusion pressure. So they had the arm at heart level, they moved it above, which decreased perfusion pressure, decreased muscle blood flow again at a constant motor drive, and looked at the force output that was generated by that constant electrical stimulation. They did the opposite. They moved the arm below heart level, which increased perfusion pressure because blood is trying to move along basically the pressure gradient, so down with gravity. And what they found was that when the arm was raised above heart level at a constant motor drive, the muscle generated more force. So as more oxygen is being delivered to the cell, force output goes up at a constant motor drive, and when oxygen is being not delivered at the same rate by moving the arm below heart level, force output declined. And we know that the muscle was not fatigued as a result of either of these two, because when the arm was returned back to heart level, you can see that the force output of the muscle returned back to basically the at heart level state. Okay? So again, the muscle at a constant motor drive is conforming to the oxygen state. It'll generate more force for a given metabolic state. With more oxygen, it'll generate less force for a given metabolic state with less oxygen. So, the summary of this, coming back to this kind of model, is that at a constant motor drive, reductions in intracellular PO2 that are mediated by changes in oxygen delivery, either the amount of oxygen content or muscle blood flow, will result in a decrease in oxidative ATP production and force output without perturbations or stimulation of the other drivers of ATP provision. So, therefore resulting in a disturbance in muscle metabolic state. So increases in ADP and PI, which have increases in PI have obvious effects on muscle fatigue development. Also, increases in ADP concentrations will stimulate glycolysis, which will increase the rate of development of intramuscular acidosis through the development of lactic acid. The alternative is true, is that at a constant motor drive, increases in intracellular PO2 will allow the muscle to generate more force produce more ATP aerobically without any change in these other substrates of oxidative phosphorylation, which are dependent on phosphocreatine breakdown and stored ATP breakdown and glycolysis. Okay, so the muscle will conform to the oxygen state of the cell, which in turn is dependent on the rate of oxygen delivery. So alterations in oxygen delivery evoke changes in intracellular or muscle PO2. Muscle adjusts its force production and power output to conform to the oxygen delivery at a constant motor drive, and importantly, muscle metabolic environment is unaltered under conditions of constant motor drive. But that's not how we exercise. We don't have electrical stimulators activating our muscles for us. We have our central nervous system that does that. So we have voluntary exercise, which is very different than obviously these experimental conditions. This then leads us into the net drive hypothesis that we talked about. So this is, again, a summary slide from last time where we have the mass balance equation for oxidative phosphorylation. We have the substrates for oxidative phosphorylation producing ATP. We know that ATP supply and demand must be met in order to generate a given force output. Stimulation of glycolysis through the increase in ADP concentrations can liberate hydrogen ion, which again can contribute to fatigue, but certainly increases in intracellular inorganic phosphate levels have pretty pronounced effects on the rate of fatigue development. So the goal, of course, is to try to provide most of the ATP needed to match ATP in supply and demand through oxidative phosphorylation. But if that's not possible, you have to upregulate the other ATP supply systems, but that comes at a metabolic consequence. Okay? So, I showed you this particular evidence again from Michael Hogan's group, where they did that 31 PNMRS study, where they did the calf plantar flexion exercise, incremental exercise, and if I remind you here, they did this under 3 different FiO2 conditions. So they did a pretty severe hypoxia condition, so just 10% inspired oxygen, a normoxia condition, so 21% oxygen, so room air, and then they also did a hyperoxic condition, so 100% oxygen. So now they're manipulating oxygen delivery by changing arterial blood oxygen content. And if you remember, in the hypoxic condition, you can see that the rate of decline from its baseline value in phosphocreatine was much more accelerated in the hypoxic condition than it was in the normoxic and in the hyperoxic conditions, such that at any given power output, at any given level of ATP demand required, right? Because ATP demand is going to be matched by, or is going to be determined by the external power output requirements. So at any given power output, in hypoxia, you can see that the extent of phosphocreatine degradation is much greater. So to try to protect the muscle and maintain that balance between ATP supply and demand, there needs to be greater phosphocreatine degradation at the site of ATP utilization. And this was attenuated to a much greater extent in the hyperoxic condition. With the opposite being true, is that at a standardized power output, you can see that the amount of inorganic phosphate accumulation relative to baseline was much greater in hypoxia compared to hyperoxia. But the interesting thing, and the important take-home message here, is that at the point of exhaustion, when the calf could not plant or flex anymore, the muscle metabolic state in terms of the extent of phosphocreatine degradation and accumulation of inorganic phosphate were nearly identical. So, the oxygen status of the cell will determine how long it takes for the muscle to reach that critical metabolic state, where the demand for force output can no longer be met for the requirement for force output. And you'll remember, and you'll see it, it's going to come in one of the first couple of lectures that I showed of those constant load and incremental exercise where the dashed descending line and ascending line intersect. You should be able to transpose and think about these ideas now in that context and almost see it. Okay, so that's what I'm hoping to achieve by the end of this lecture. And again, the time to exhaustion was different. Prolonged in hyperoxia compared to normoxia, and shortened in hypoxia compared to normoxia. So, the duration of exercise, which is, again, a function or a determinant of exercise performance is dictated in part by the oxygen status of the cell. So, I did not show you this, but I think this is a really, really cool study. And it has implications for some of the exam questions and things like that that you're going to answer or be expected to answer. And we'll go through at the beginning of next class a little bit of an exercise to try to bring all these concepts together. Okay, so there'll be a handout and you'll basically have to draw the temporal patterns of all of the different metabolites and motor drive and ratings of perceived exertion over time doing manipulations of blood flow or oxygen delivery. So we'll go through 3 examples of that at the beginning of next class. Okay? I will not record that lecture. So you show up, you benefit. You don't, you don't. It's the way it works. So if you're here, to all those people that are going to be listening to this on YouTube, you show up on Thursday, you get the review. If you don't, it is what it is. But I'm not going to record that lecture. So, the experiment in this particular study is this. Human subjects, again 6, perform steady state submaximal exercise at 60% of their peak power output. So again, if you could generate 100 watts of calf plantar flexion exercise, you exercised at 60 watts. Okay? And this was done again under 3 different FiO2 conditions. So normoxia, hypoxia, hyperoxia. So control, low, and high oxygen. And again, they measured changes in phosphocreatine and inorganic phosphate levels using this radio-labeled magnetic resonance spectroscopy device. Okay? So, super cool study. Shows you the temporal or the time-based kinetics of changes in intracellular or intramuscular the metabolic state in responses to manipulations in oxygen delivery at a constant voluntary motor drive or a constant exercise intensity. So here I'm showing you in each panel the percent change in phosphocreatine in the rest to exercise transition under different oxygen conditions. So, in this first condition, what I'm showing you, in going from rest, at the onset of exercise, you can see in every single condition phosphocreatine degrades, right? We know that that's a part of the bioenergetic pathway. You need phosphocreatine degradation because part of that is a means of turning on or providing the precursing elements to activate oxidative phosphorylation as well as glycolysis. So we know that these things occur basically in a time-based sequence. So phosphocreatine degradation is a normal response. So you can see here that phosphocreatine degrades, but if you go from hyperoxia and midway through the exercise here, at about 5 minutes of constant load plantar flexion exercise, you switch from breathing 100% oxygen to 10% oxygen. Look what happens to the phosphocreatine levels to maintain the same force output. Phosphocreatine levels will actually decline and relatively quickly. So now you've decreased the amount of oxygen going to the muscle, but the ATP demand is the same. The force output requirement is the same. So the muscle's like, shit, I can't generate this ATP through oxidative phosphorylation, at least at not the rate that I need. But I need to protect ATP supply and demand. So start breaking down phosphocreatine. And look, phosphocreatine drops. It's a pretty sensitive intramuscular system, eh? Like, that's a pretty quick, think about how quickly we can measure it. It's probably happening much faster than this, but this is just how we measure it. Well, they measure it and analyze it and average it. But it's probably happening much quicker than that. And then as soon as they stop exercising, look, right back to recovery. So the phosphocreatine levels go right back up to normal levels. Go the other direction. Now in hypoxia, at the rest to exercise transition, a much greater degradation of phosphocreatine in the hypoxic state. If you're starting exercise without much oxygen in the cell, you need to rely more in the rest exercise transition on phosphocreatine degradation. And as soon as they switch from hypoxia to hyperoxia, look, it then recovers. So now you give it a little bit more oxygen, it supplies that ATP through oxidative phosphorylation and relies less on phosphocreatine degradation and can recover itself a little bit. And interestingly, because it is steady state exercise, it recovers to the level that was achieved in the hyperoxic state previously. So again, there's a really, really precise matching of the metabolic demands and the ATP providing machinery based on the oxygen state of the muscle. So now go in the other condition. Here's the normoxic condition. So this is kind of like the room air control. Exercising here for 10 minutes, phosphocreatine degrades, reaches steady state plateau, and then it recovers. So now you go here, the hypoxia to normoxia condition. You start with low levels of oxygen, greater phosphocreatine degradation. You move right back to normoxia, goes right back to the normoxic level within 5 minutes. This is cool stuff. Like, I don't know, like, this is cool. Because it all, like, fits. It all makes, like, if this experiment wasn't showing this, then all these lectures wouldn't, but these are really cool experiments. I don't know if you guys never done research, but this stuff is pretty cool. So you see that oxygen again levels decline, and now you move from a switch from hypoxia to hyperoxia, and again, it's below the normoxic level and then it rises above. So greater phosphocreatine degradation to protect ATP supply and demand, or match ATP supply and demand at the level of the muscle in the hypoxic condition, and then it doesn't need to protect it quite as much in the hyperoxic condition. So you can see that these changes are all occurring in relation to the normal oxygen state. So this is going to have implications too as we start working through some of the examples at the beginning of next class. Okay? Because for example, if I give you a question, what is the inorganic phosphate or phosphocreatine levels going to look like relative to baseline? Say if I do a switch in muscle blood flow, that would increase muscle blood flow from this point. So you would have to be able to say is that if I could increase muscle blood flow, then say phosphocreatine levels would increase above that steady state level from when there was normal muscle blood flow, but it certainly wouldn't return towards the baseline level. So my point is, it's a little bit of a confusing statement. The point is that you're going to have an appreciation for the magnitude of changes relative to baseline, as well as pre-existing kind of steady state levels. All of that will make sense at the beginning of next class. Okay? So I think the key here is that during steady state submaximal exercise in humans, phosphocreatine levels as an immediate source of ATP provision adjust to compensate for changes in intracellular PO2 to maintain a constant oxygen uptake and force output. This is direct experimental evidence for what we're referring to as the net drive hypothesis. So, in summary, how does the VO2 and force output get maintained during voluntary exercise when oxygen delivery is reduced? So at a constant ATP demand or a constant ATP level of production and force output, if intracellular PO2 levels decrease, we have to actually recruit bigger and more motor units to support that force production. And if the example with Omar, that's going to have a sensory consequence. You drive the muscle harder, it's going to be perceived as more difficult. But that's also going to come at the expense of greater metabolic perturbations. So greater activation of glycolysis through the phosphocreatine breakdown is going to increase things like ADP, inorganic phosphate. So you're going to have an increased rate of lactic acid production, intracellular acidosis, as well as increase in intracellular inorganic phosphate levels, which will directly impair muscle contractile function. The opposite is true, is that at a constant ATP demand or force output in the setting of an increased intracellular PO2, so through increases in oxygen delivery, is that you can get away with a reduced motor drive, so less central nervous system activation of the muscles to support a given force output at lesser of a metabolic disturbance, which means that you have a decreased stimulus for the activation of glycolysis and a slower rate of accumulation of inorganic phosphate. Therefore, you would have a slower rate of development of peripheral muscle fatigue. You would be able to maintain a given force output for a longer period of time, and that would be an indication of enhanced exercise performance. So, alterations in oxygen delivery evoke changes in intracellular PO2. During voluntary exercise, we know that motor drive or recruitment of a muscle can increase in order to maintain force production, but this occurs at the expense of higher ratings of perceived exertion. Inorganic phosphate directly affects muscle contractile function through these various mechanisms that we've talked about in detail. And increase in intracellular ADP and PI levels stimulate glycolysis, which will increase the rate of lactic acid production, which again may or may not be directly linked to muscle fatigue, but is certainly a signpost or an indicator that exercise intensity is at a level that's not sustainable for much longer. So, coming back to some of the introductory lectures to try to bring all this back together. Remember that human performance is ultimately a reflection of muscle power output. If you're going to exercise for 5 minutes, the person that's going to have the greatest performance is the person that's going to be able to maintain the highest mean power output for 5 minutes. Alternatively, so basically the higher the muscle power output a person can sustain for a given time or distance, the better their performance will be. So this has direct implications for 5 kilometer, 20 kilometer, 60 kilometer time trials, marathons, swimming events. Everything operates like this. Like I gave you the example, trying to go to the grocery store and trying to collect all your groceries in as quick as time as you can. The faster you walk, the more materials that you can lift and carry, the quicker you're going to get your grocery shopping done. This is not always just about athletic performance. There's other implications. So muscle power output depends on muscle metabolic and contractile function, which in turn depends on bioenergetics and the factors governing its control, oxygen delivery and intracellular PO2. I think that's verbatim from the slides that I put on in lectures 1 or 2. So trying to bring all this back together and show you the links from earlier classes to now. So, again, as a review, human performance, maintaining the highest muscle power output for a given distance or time. So if you remember, this is the power duration curve. So, the power duration curve basically represents the amount of time that a given power output can be sustained. So if we did a series of repeated exercise tests, let's say that we did an exercise test at, say, 800 watts on a cycle ergometer. We would only be able to sustain that power output for a very, very short period of time. So we do one super maximal exercise test, and then another test, another test, another test, another test. And we would develop a power duration curve for an individual person. And so you can see here that basically as the time point at which power output cannot be sustained for any more time represents a performance limit. So these stars represent the time at which you can no longer maintain that power output. So either you would have to stop or decrease your power output in order to keep going. Okay? So we know that as muscle power output decreases, exercise duration or sustainability increases. But again, we want to maintain the highest power output for the longest time or over a given distance or time as a measure of exercise performance. So ideally we would want to operate at the highest power output for the longest period of time possible. Okay? So if we look at human work performance during constant rate exercise, here we have people exercising at a fraction of their peak power output. Remember, the dashed line represents the peak power output that the muscles are able to perform, where the solid line would represent the power output that is required to perform a given physical activity. So, the performance limit is reached when these two lines intersect. So if you're going to exercise at 75% of your peak exercise capacity, your muscles will fatigue, their force generating capacity will progressively decline, up to a point where the demand for force output intersects with the capacity for force output, and that will dictate your performance limit in terms of time. And so along the power duration curve, this would fall, for example, somewhere here. If your peak power output is 800 watts, 75% would say represent somewhere around there, and so your exercise duration would say be 2.5, 3 minutes. Now, if you were to exercise at 50, remember, the slope of the dotted line reflects what we're calling the rate of development of fatigue. You should be able to think now to those Hogan studies. The rate of inorganic phosphate accumulation and phosphocreatine degradation, right? The slopes were different when you changed the oxygen delivery state. Exercise endurance time was longer in hyperoxia than hypoxia. It's the slopes of these lines in conceptually, but those were experimentally shown. So if you exercise at 50% of your peak fractional power output, you're going to be exercised longer because you just moved down that power duration curve to a more sustainable power output. And if you were to walk, you can walk all day. Okay? So, to bring this back to light, if this is your normal oxygen delivery state, increasing oxygen delivery in intracellular PO2 will slow the rate of development of fatigue and allow you to achieve exercise at a given power output for a longer period of time. If you compromise oxygen delivery and decrease intracellular PO2, you have to have other metabolic adjustments that support ATP supply at the site of demand. But that comes at the expense of muscle metabolic disturbances, which lead to a rate of accumulation of fatigue-causing metabolites and an earlier cessation of exercise. So you reach that point of intersection between what the muscle wants to do and is capable of doing earlier. So oxygen delivery and intracellular PO2 dictate the time it will require, how long you'll be able to exercise at a given power, because it changes the rate of accumulation of fatigue-causing metabolites in the muscle, as I showed you experimentally in the previous slides. So what happens with incremental exercise? Where now we have an incrementing demand on the muscle and a progressively declining capacity of the muscle to support that demand. So exercise intensity increases, say, every 2 minutes, like you did in, I think, lab number 1 as an example, 25 watts every 2 minutes to the point of symptom limitation. The muscle progressively fatigues, and at that point of intersection, where the muscle cannot support that force output anymore, you reach a performance limit. Performance limit will be improved if you can slow that rate of fatigue development and achieve a higher power output exercising for a longer time. The opposite is also true. So, this is what would happen if you manipulated oxygen delivery. Increasing oxygen delivery would slow the rate of fatigue development by slowing the rate of accumulation of inorganic phosphate, hydrogen ion, phosphocreatine degradation, and those precursors to drive glycolytic flux to support ATP supply and demand. That would allow you to achieve a higher exercise time and exercise to a higher fractional power output. If you compromise oxygen delivery, which often happens in states of disease, emphysema compromised oxygen delivery by impairing gas exchange at the lung, often leading to arterial hypoxemia. Vascular abnormalities, peripheral artery disease, coronary, like congestive heart failure, pulmonary vascular disorders will result in compromisation of skeletal muscle blood flow. You decrease blood flow, you decrease oxygen delivery. Decreased oxygen delivery decreases intramuscular PO2. Increased reliance on other metabolic pathways to support a given increase in exercise intensity. And as a result, you have to stop exercise earlier. So, now with that kind of like as a quick summary, I'm going to show you some experimental evidence that I hope brings all of this together. So these are, I get excited about these. So these are studies that come from this guy Jerry Dempsey. I think I mentioned his name at the end of last class. He's recently, well, relatively recently retired, worked at the University of Wisconsin-Madison. And he's, I mean, if you're interested in kind of like a physiology career trajectory, and you know what you start doing and what you end up doing are being two completely different things. This is a guy that started off research in the 60s looking at obesity, and then he moved into altitude expeditions and acid-base balance and cerebral spinal fluid, like basically punctures, looking at acid-base renal and respiratory accommodation adaptations to altitude. Then he moved into things like female sex hormones, and then sleep apnea, and then exercise physiology, and breathing mechanics, and flow limitation, and worker breathing, and the respiratory muscle metabolic reflex. And was the first guy to basically stick an epidural anesthesia into the spine of exercising athletes to look at the role of respiratory peripheral muscle mechano and metaboreceptors and feedback-mediated vasoconstriction of exercising muscles, and anyways, amazing career. So he's gone from animals, done basically cross circulation, change the circulation, basically take the circulation from an animal, ventilate it through a peripheral lung, and then put the circulation back into an animal to look at what would happen if you basically manipulated blood flow and gas exchange through different lungs and different circulatory systems, so that you can really, really control what the muscle sees versus what the lungs see. Really, really cool research that he's done. But these are some studies that he did with a guy, Marcus Amen, who's now at the University of Utah, working with a guy, Russell Richardson, that's looking at some really cool research about muscle metabolic adjustments and fatigue development and things like that. So this is a series of studies that I'll show you looking at the effects of altered oxygen content on central motor drive, peripheral muscle fatigue development, exertional symptoms, and exercise performance in healthy adults. By healthy adults, these are basically elite cyclists. Okay? So, the experiment here that they did about a decade ago was they took 8 trained cyclists, so VO2s of about 65 mils per kg per minute, so these are very fit individuals. Males completed 3 constant load cycle exercise tests on the cycle ergometer at about 315 watts. So, most of you probably couldn't, and this is no offense, most of you probably couldn't achieve a peak power output of 315 watts. So this is what they're exercising at as a constant rate. Okay, so this is their sub-maximal exercise intensity. Equivalent to about 82.5% of their peak power output. Okay, so this is what they're being asked to sustain. Now, this is a very, very important aspect of this trial, is the experimental design. So I want you to really appreciate what they did here. The first trial was performed while breathing the hypoxic gas. So basically they did the first trial in the condition where oxygen delivery would be the most compromised, assuming that that was going to be the state at which exercise duration was going to be the most compromised or the shortest. Okay? So the trial was performed while breathing a hypoxic FiO2 of 15% until exhaustion. This corresponded to an arterial oxygen content of 18 mLs of oxygen per deciliter of blood. This is very important. In trials 2 and 3, they time matched the trials to the individual time that was performed in each of the 8 athletes at basically when they were hit exhaustion in the hypoxic trial. So whether or not they could go longer in normoxy or hyperoxy doesn't matter. If they exercise for 6 minutes in hypoxia, they stop them in the normoxy and hyperoxia at 6 minutes. This is a really, really important aspect of this trial because it allows somebody to not evaluate what's happening at the peak of exercise, but at a standardized submaximal time during exercise. And I'll show you what that means graphically. So they did this breathing the normoxic gas or the hyperoxic gas, so room air and 100% oxygen. Peripheral quadriceps fatigue was assessed by changes in pre versus post-exercise force output in response to a supermaximal magnetic femoral nerve stimulation. So basically they take a big figure-of-8 magnet and they shove it into the groin. They stick the leg, I'll show you a picture, but they stick a leg, there's a person sitting on a bench, they stick a leg in a device where the leg is on a force transducer and not able to move. And they shove this figure-of-8 coil in the groin and they stimulate it, and then the leg tries to kick, kind of like a reflex because you're stimulating that motor nerve. The leg tries to kick but doesn't move, and it generates a force output. So the amount of basically maximal force contraction of the quadriceps. Okay? So it's an isometric contraction, but electrically stimulated to recruit all the motor units is the idea. They also measured central motor drive during the trials using EMG activity of the vastus lateralis. So basically during the exercise, what's the activity of the muscle, the neural activity of the muscle? As the EMG activity goes up, it's an indication that the brain is recruiting more motor units to support a given exercise intensity. Okay? So, graphically, to show you, they exercised in the hyperoxic condition at 314 watts, and this corresponded to an average of about 270 seconds of exercise. Then, they did the exact same duration of time in normoxia and the exact same duration of time in hyperoxia. So now they're able to make comparisons of the oxygen delivery state at standardized times. The comparisons wouldn't be all that meaningful if they allowed the people to exercise to their point of tolerance. Because like I showed you before, at the point of tolerance, presumably when you can't exercise anymore, the muscle metabolic state is the same. So you couldn't compare at 270 seconds, 350 seconds, and 450 seconds. You would have to compare all the measurements at 270 seconds to really see what the effect of manipulating oxygen delivery or content are on muscle metabolic performance. So here's an example of the setup. You can see that they have a person sitting with their leg at 90 degrees. They've got basically an electrical stimulator stuck here at the femoral nerve. They've got this force meter strapped to the leg that doesn't move, and then when they send an electrical impulse, they shock the nerve. The leg tries to kick, but it doesn't actually move, and the force that the muscle, basically the leg extension, will be generated here by a force transducer. And then what they do is they look at how fresh the leg was, so basically how much force was produced before exercise compared to how much force was produced after exercise. And if you get a post to pre loss in force output, it means that the muscle is fatigued. You've maximally recruited the motor nerve, and if the force output declines, it means that the muscle has basically fatigued. It can't generate force in response to a given electrical stimulation. So generally a loss of about 15% of force output from pre-exercise levels is considered objective evidence of peripheral muscle fatigue development. Okay? So here's a summary of the results. So the effects of changing oxygen content on peripheral muscle fatigue development. So now, they all exercise for 270 watts of the different oxygen conditions. So if you look at the quadriceps twitch force as a percent change from pre to 2.5 minutes post-exercise. They exercise for the exact same period of time. In the hypoxic condition, they lost 25%, almost 30% of their force production. Maximal nerve stimulation, they lost 25% force production. So the muscle at 270 watts is pretty fatigued in the hypoxic condition. At the exact same time, in the normoxic condition, the loss of force, or the amount of fatigue developed at 270 seconds was not as much. And it was attenuated further by hyperoxia. So the rate of fatigue development was more exaggerated in hypoxia than in hyperoxia. If you look at the integrated EMG activity, so how much did the muscle need to be recruited to support that 314 watts for 270 seconds? You can see that in hypoxia, the central nervous system needed to recruit much more aggressively the quadricep muscle, or the vastus lateralis, than in normoxia versus hyperoxia, in order to sustain the exact same power output for the exact same period of time. You should be seeing that net drive hypothesis example of changing with the increase and decrease in oxygen delivery. To support a given ATP demand, PCL02 goes down, motor drive must go up, but that's going to occur at the expense of muscle metabolic perturbation, which is going to contribute to greater fatigue development. And if you look at the ratings of perceived exertion, the hypoxic exercise, again, the same power output done for the same period of time, is much more uncomfortable when there's low levels of oxygen than when there's high levels of oxygen. So this is direct experimental evidence for the net drive hypothesis. To support a given power output, you have to recruit the muscle more aggressively, which has a sensory consequence of more ratings of perceived exertion, but at the expense of a greater rate of development of fatigue. So changes in oxygen content during exercise at a given power output affects the rate or magnitude of peripheral muscle fatigue development, and changes in oxygen content affect the amount of motor drive required to achieve a given power output, and therefore the ratings of perceived exertion. So the same task is perceived as being more difficult if you compromise oxygen delivery. Is perceived as being less difficult if you improve oxygen delivery. So let's bring this back to this example again. To perform 314 watts for 270 seconds, remember, the slope of the dashed line represents the rate of muscle fatigue development. In normoxia, it delays the rate of fatigue development, and hyperoxia does it even further. So the implications then is that if in the normoxia condition you would have been able, this person would have been able to exercise to say 400 seconds before they reach this performance limit. And in hyperoxia, they would have been able to exercise, say, to 500 seconds before they reach the performance limit. So the difference so these really reflect differences in the rate of muscle fatigue development. So during normoxia and hyperoxia versus hypoxia trials, again, subjects would have been able to continue exercising at that power output for considerably longer. And if you want direct experimental evidence of that, you can go to slides 31 and 32, which I'll get to, obviously, later on in this lecture. But it'll show you that exact same experiment. They did the exact same thing, but they did an endurance time trial, and they found exactly that. They could exercise longer at that power output when oxygen was high compared to when it was low. So, bringing this back again, at a given or constant ATP supply or demand and a constant force output of, say, in this case 314 watts, compromising oxygen delivery necessitated an increase in motor drive, so recruitment of the muscle. There was presumably an increase in the other drivers or substrates of oxidative phosphorylation, which are coming from breakdown of stored ATP, phosphocreatine degradation, ultimately to try to stimulate glycolysis to support that ATP supply and demand. This will drive glycolysis, result in a greater rate of accumulation of hydrogen ion and lactate ions, as well as a greater rate of accumulation of inorganic phosphate. You will also have an increase in exertional symptoms as a consequence of greater recruitment of those muscles. At a constant ATP demand and force production, increasing oxygen delivery will allow you to get away with less motor drive to support the same physiological task, and less of a muscle metabolic perturbance or disturbance. And also with fewer exertional symptoms. So, here's another study. Now, this is now a switch of the paradigm. Now, that was constant load exercise, where I bring, what's your name? Sam? I bring Sam into the lab and I say, Sam, exercise at 314 watts for 270 seconds under these three conditions. Okay? So now what I do is I do something that's much more performance-based. I bring Sam into the lab and I say, Sam, you're going to do a 5-kilometer time trial. Simple. Complete 5 kilometers as fast as you possibly can. That's it. It's not that simple, but that's basically what I'm going to ask him to do. Complete 5 kilometers as fast as you can. Now, Sam's goal is to try to maintain, therefore, the highest power output he can over 5 kilometers, right? Generate more power, you move more quickly through space, he finishes 5 kilometers faster. So if he maintains an average power output of 300 watts compared to my 200, he will complete 5 kilometers quicker than me. He wins a gold medal. I'm eating Cheetos in the basement with my grandma. Okay? He's a millionaire. I'm working at McDonald's. Okay? So, real implications for these types of things. So this is a 5-kilometer time trial. Now, you have the key here is that in the constant load exercise, I control what Sam does. In a time trial, Sam controls what he does. So now Sam can take advantage of all the little feedback loops and everything, the muscles getting fatigued. He can pace himself now. He can increase or decrease his power output if he feels good, feels bad. Okay, so that's the key to these two different experiments. So these again are 8 trained males perform 5-kilometer cycling time trials where the power output can be adjusted voluntarily in 1-watt increments. Under the different oxygen content conditions, again, same thing, hypoxia, normoxia, or hyperoxia. They looked at fatigue, muscle fatigue development using the twitch stimulation. Motor drive was assessed by EMG. And they also, in this study, performed a constant load exercise test, this time to exhaustion, not stopping at 270 seconds, but to exhaustion at 314 watts under the different conditions. Okay? So 2 separate studies. Time trial is the focus, but then they also did an endurance time to exhaustion during constant load testing. So this is really, really cool stuff if you can kind of see all of these hypotheses begin to work together. So in the upper panel, worst time for my laser pointer to die. On the upper panel, the integrated EMG activity of the vastus lateralis. Starting from time point 0 through to 5 kilometers. And on the bottom is the power output. So basically the force being exerted on the pedals, right? So, normoxia condition, this doesn't mean anything without the comparison. But basically, you can see that right out of the gates, they fire out of the gates, they generate a very high power output of nearly 400 watts, and like, shit, I cannot maintain that power output, so they get into their pacing after about 1 kilometer, and they reach a nice little steady state. And once they see that 4 kilometers, they got that last kilometer, they power through, and they cross the finish line, in this case in 458 seconds, with that amount of EMG activity or muscle recruitment. Now, in hyperoxia, even at the onset of exercise, they're blinded to the oxygen condition. They come out and they're already generating higher power outputs. They get into the same pacing strategy, but over the course of the time trial, they maintain a higher power output. They can maintain a higher muscle activation to support that power output. And as a consequence, they complete that time trial. They complete that time trial in almost 20 seconds faster. Now, bleed in a little bit of hypoxia. Look at the compensation that has to occur. They deteriorate their power output pretty dramatically. They don't have the same post-exercise sprint. And they complete exercise now almost